So today we're going to get into logarithms, which is mainly what this unit is about, although you'll see that logarithms and exponents are very closely tied together. Have you seen logarithms before, anywhere? No? Like heard of them kind of thing, but never really used them in a class or anything? A little bit where?
In computer science, I'm not sure if it's directly related, but we were talking about a certain way of interpreting how a algorithm in programming will run and how fast it'll go.
Yeah.
One of the notations we use is O log n, which
Yeah.
we'll actually explain.
Yeah, interesting. Okay, there you go. So maybe you'll understand a little bit more after a few days of doing this stuff, but it's interesting. Okay, so the next 3 days, today, Monday, Tuesday, we're looking at just kind of evaluating logs and understanding logs and some of the properties of logs. That's what we're going to do. Then we're going to spend a few days solving equations with them, or a couple of days at least, a couple of days on applications. And I think I said this the other day, our test on this will be the Thursday before the break. We've got 2 weeks left before that. So that's that. And today, over these next 3 days, one of the main things you really want to get familiar with is the notation. You really, really, really need to nail that and get familiar with that. And like anything that's brand new, it's very different at first, and you got to really wrap your mind around it. And actually, remember all the way back at the beginning of the course when we started talking about radians. And I use that analogy, it's like learning a new language, where in the beginning, you're always translating the new language to a more familiar language, thinking in that language. So if you're learning French for the first time, you translate everything to English, think about it, come up with your answer or whatever, your response, translate that to French, and then deliver that as your response, right? And we did the same thing with radians. You probably kind of remember that. And so I think with logs, it's very much the same. We're going to do a lot of thinking about logs in terms of exponents today until we get familiar with them. But ideally, by the end of the unit, you want to be thinking in logarithms. Hi.
Hi, is my name here?
Yes.
Sorry.
You want to be thinking in terms of logs by the end of the unit. Okay? And so that's something to keep in mind. So, before we get started, how many operations can you name? Somebody name a mathematical operation. Multiplication. Okay, so this would be something like 5 times 3. One thing that's interesting about multiplication is it has the property that it is commutative. Have you ever heard of that before? So if you study math beyond high school, they start to talk about the deeper levels of mathematics. And all of these fundamental theorems that we sort of take for granted, or that we define as true, and then we build math from there. Anyway, it's complicated, but so you start talking about operations, perhaps, and the properties that they have or that they don't have. So, like distributive property is one, and multiplication has it, but addition doesn't. Like if you had addition, you wouldn't use distributive property on that with brackets, right? That wouldn't make any sense. That's something anybody's ever thought of before. Right? So some things are distributive and some things are not. Interesting. Anyway, commutative is a property where if you flip the parts, the arguments, which we would call like 5 and 3 sort of the arguments of this operation, it's the same. So 5 times 3 and 3 times 5 is the same, right? So some operations are commutative, some are not. And we kind of take that for granted, but that's probably something that you sort of know. So 5 times 3 is going to be equal something, right? We could evaluate that. 3 times 5 is going to give me the same thing. How do I undo multiplication? So how do I do this? So anybody know what 3 times 5? Just kidding, no. So if it's 15, how do I find division? Right? So sort of the undoing of multiplication is division. So 15 divided by 5 equals question mark. That's sort of the same as like when you learn multiplication first in elementary school, and then your teacher probably didn't even know what was happening, but they tricked you and they started asking you questions like this. Well, what number would you multiply 5 by to get 15? And most people can solve that by inspection and get 3, and they're actually teaching you how to divide before they even tell you what division is, right? But they're connecting those ideas. It's a really important concept in mathematics to make those connections. The same with adding and subtracting, that kind of thing. And then they teach you actually how to divide. Division's not commutative. 15 divided by 5 and 5 divided by 15 are not the same, right? So some operations are, some operations aren't. Okay? And I could do the same thing here. What if I put the question mark here? Some number times 3 is 15. Solve it by inspection. Or learn a new operation to calculate it, which is helpful to have an operation like division to solve it, because then we can do it when it's not obvious. You know, if it's a decimal or some kind of nasty number, we can just calculate it as opposed to solving it by inspection. Okay, so then what about, let's say, addition? 5 plus 3. Okay, 3 plus 5, same thing. So 3 plus something is 8, or something plus 5 is 8. And so then again, you know, that's connected with subtraction. Addition is commutative, subtraction is not. Those things. Can anybody name another operation? So we've got multiplying, dividing, adding, subtracting. Okay, subtraction, yes, that one goes with this. So this would be like 8 minus 5 equals something, or 8 minus 3 equals something. So those are kind of all the different exponents and roots. So this is interesting. Exponent is another kind of operation, although it's just a different way of writing repeated multiplication. Although you could also say multiplication, it's kind of a different way of writing repeated addition. But anyway, very good. Exponents is another one that we know. And then roots is actually just a different way of writing exponents, but it's still kind of like, so you could kind of think of it as the same thing, or you could kind of think of it as separate. Very good. So 3 squared is something. And 3 squared is different from 2 cubed, so exponents are not commutative, right? Order matters. 3 to the 2 and 2 to the 3 are not the same thing. And this is really interesting. Megan, it was perfect that you said that, because that's leading exactly where we want to go. So if I do this, I have room here. Okay, so if I'm thinking about these, if I do this, the square root of 9 question mark, or some number squared is 9, right? That's undoing that. See what I mean? So I've got the question. If you look back at these ones, I took this question mark and I put it everywhere else. And so we can use division to find these question marks. Right? I took this question mark and I put it here and here, and now I can use subtraction to find those question marks. And so then 3 squared, I use exponents to figure it out. But what if I already know the square and I already know the result? So I know the 9 and I know the square. Well, I would use a square root to find that question mark, right? See what I mean? So here's the thing. In all of high school, even though you learned exponents a long time ago, we don't know how to find that question mark. I mean, you know by inspection, and again, we do that originally, and in fact, you have a whole system in grade 11 that you learn that you can solve questions like this when this is like a perfect power of the base, so 9 or 27 or 81, you could solve it. Anybody remember how to do that? So if I rewrite 9 as a power of 3, rewrite them with the same base, and in this case it's kind of trivial, you would just maybe state the answer, but there are harder questions. Yes, absolutely. Right, there are harder questions that require a little bit more work, and you rewrite them in the same base. And we're going to do some of this practice today, actually. But it would be something like, so 3 to the x equals 3 squared, therefore x equals 2, right? That kind of thing. equating, rewriting with the same base, and then equating the exponents. If the bases are the same, the exponents have to be the same, that kind of thing, right? So we solve it by inspection. But just like everything else, since, I don't know, grade 1 or something, we always kind of start with that, but then we learn the operation to actually do it. Okay, so here we go. Let's take a look at this. 5 squared, there's my question mark. I can solve this when it's 25. I don't know if you really have to write this down. You can if you want. Some number squared equals 25. So that's like the square root of 25 equals 5. So I can evaluate that one with square roots or rewriting it as an exponent to the 1/2. This is the one that we don't know how to do. Now I know that my question mark in this case is 2, but that's just by inspection. Can anybody tell me what the question mark is in this next one? 2 to the question mark equals 32. Who knows what that one is? You might just know some of these powers, and in this unit you should hopefully get more familiar, and you've got to start to recognize some of these things.
5.
Is it 5? So 2, 4, 8, 16, 32. It's 5, very good. And if we were solving this the grade 11 way, I'd go 2 to the question mark. Question mark's like an X, right? Isn't it interesting how we like, X is this big thing. We're always solving for X. We're always solving for X, but it's just like a question mark. It's just, this is the thing we're trying to find. We call it X all the time. Anyway, 2 to the 5. So therefore, my question mark equals 5, right? That's just the way, because 2 to the 5 gives you 32, just solving by inspection. What about this next one? Any ideas? Why is this one harder? John? Right. 100 is not a perfect power of 6. So what does 6 do? 6 times 6 is, everybody knows this one? 36. What's 36 times 6? Who's got the calculator handy? 216. So we jump from 36 to 216. Right? 100's in there somewhere. So if I don't know, in some people even do it this way. In an elementary school, you probably kind of start like this. We'd be like, well, 6 to the 2 is 36. 6 to the 3 is 216. So now I have to start guessing at numbers in between there. So what's 6 to the 2.5? Somebody help me out. Yep. 88.2, that's good enough. What's 6 to the 2.6? 105.5. Okay, so I've narrowed it down a lot. What's 6 to the 2.57? Rounds to 100, so 6 to the 2.57 is approximately 100. It was 99 point something, something, something. Okay, so, I could try a bunch of different ones and narrow it down and squeeze in and get closer and closer, but what a pain that is. Like, who would want to be doing that, right? So, wouldn't it be nice if there was some operation that could calculate the exact value for us? Oh my gosh, let's call them logarithms. And let's learn something about them. So this is important. Remember what I said today is all about notation, getting yourself familiar with the notation. You're going to be doing a little bit of evaluating, but it's really just getting used to the notation. And then over the next few days, and the next week, we're going to learn how to actually evaluate logarithms and some of the different properties we can use to do things with them, and then get into some equations. In every unit so far in this course, we've done a lot of graphing. In this one, we're not going to do as much because logarithmic graphs, like exponential graphs, are kind of mucky and messy, and they're not as useful or not as interesting. We'll look at them a little bit, but not as much as we have in the other units of this course where we've done a lot of graphing. So take a look at these two. 6 squared is 36. We agree that's all true. We already kind of talked about that. Everybody agrees that's true. But look at this one. That's how we write a log. So this is a correct statement, this statement on the right. What's the relationship between those three numbers that you're given here? Like somebody look at those three numbers and tell me, what is the relationship? I'll give you, just to help you think, is it 3 to the exponent 81 equals 4? Because if you just cover up the log, that's what it looks like. Is that true? Does anybody believe that that's true? 3 to the 81 equals 4? I hope you don't think that's true. So it's not that. Emily, you had your hand up. Okay, interesting, yeah. 81 cubed rooted is around 4. Very good. 3 to the 4 is exactly 81. Which actually means if we take the 4th root of 81, we'd get 3. Exactly. I think you're right. Vice versa might be close, but so this is like if you're not sure if this is true, check it on your calculator. It is. 3 to the 4 is 81. 3 times 3 is 9. Times 3 is 27. Times 3 again is 81. So that works. So there's the relationship between a logarithm and an exponent or power. And this is what you need to get familiar is how to rewrite. But take a look. When it's 3 to the 4 and I do the exponent, my result is the 81, right? Exponent gives us this result. A logarithm starts with the result of an exponent and gives me the exponent. A logarithm, the equals on the right side, the thing that it's equaling to is the exponent in this case. That's that question mark that we were looking at. So the logarithm does what we were looking for, right? It calculates that last part of the 3 parts of a power, the base, the exponent, and the result. Okay? So now we have an actual way beyond grade 11 of calculating the exponent. So how would I try to rewrite this one. How would you rewrite 6 squared equals 36? How would you rewrite that as a logarithm? And this is where, right now, because you're seeing it for the first time, you're probably going to be always translating to exponents, thinking about it that way, and then retranslating back to a logarithm maybe, or maybe you just get your answer, right? You're going to be doing a lot of that. But eventually, you want to get to the point where you see the answers as a logarithm. You see logarithms for what they are on their own. Does anybody think they know how to write this? Go ahead, Emma. Log 6 of 36 equals 2. So it equaled the exponent. Very good. And the result of the power goes into the log. How did you come up with that? Like, what was the thinking in your mind that got you there?
I just looked at the other example and stuck with the right numbers.
Okay, just followed that pattern. Good. Anybody else have any like? Did anybody else write the same thing? Did you have a way that you thought about it? Because everybody can be different sometimes in how they think about these things. Not really. So here's my trick. And I think if all else fails, this will always work. I just say to myself 100,000 times, the base stays the same. The base of a log and the base of an exponent or of a power are the same. You might even want to make a little note like star, the base stays the same. Whereas the power is giving me this, and the logarithm is giving me that, but the base was 6 in both cases, right? You know that the base of this power is the 6. Like that's terminology you learn in grade 9, what the base of a power is, and then what the exponent is. The power is the whole thing. So this is what we call the base of the logarithm. It's got an unfortunate, it's interesting, we were kind of joking about this in the math office the other day, how like we have all these nice little ways that we show operations with an X and a plus sign and the division, and then exponents has a nice little, just write it as a little, and then logarithms, they introduce an entire word as part of the Like, it's kind of an unfortunate notation that it's got the whole word. It's not very intuitive. But anyway, see, log, there's your base. It's written like small and down low a little bit. Okay? This is called the argument of the log. That's how you could refer to it. Or log base 6 of 36 is how you could talk about it. Equals 2. So 2 is the result, which is the exponent if you're rewriting it the other way. Okay? All right, so here's what we're going to do. We're going to rewrite the following in exponential form if we need to, which we're going to do a lot of at first, and then solve. Like I said, by the end of this unit, by the test, you should be able to do this without rewriting in exponential form. Rewriting in exponential form is one way, and there's a good chance we'll test you on that to make sure you can do that as well. But not rewriting in exponential form is another way. And I've kind of said this before, that even if you have to, do it on a separate piece of paper so that I don't see it. And then it looks like you're doing it the normal way, right? Like you could just, if that's what you have to do, then do it. But the reason is because this is like an equation. It's got an x in it. So because it has an x, I can use that to my advantage. If it doesn't have an x, and it's a little bit weird to introduce an x randomly, and so it messes things up if we can't just evaluate logs for what they are. So how would I rewrite the, and you can go ahead, I would, if I were you, I would start trying every one, just rewrite it in one line on my own. Try to beat me to it. So in this case, it's going to be, what was that special trick of always remembering? The base stays the same. What's the base of the log? The base of the log is 2. So the base of my power will also be 2. And then the 8 and the x switch, right? So the x was over on the one side, so now I bring it over to this side. And then the 8 was on this side, so I bring it over to the other side. Just like that. And now it's familiar. Now it's something that we know something about. And if this was grade 11, we would do this. And therefore, x equals 3. You need the therefore because there's not really an operation that we're using in grade 11 to go from one line to the next. We're just like we're making a deduction. So we add in the therefore to sort of help with the flow. Note that this is how some people want to do it, but it's wrong. You'll lose marks. 2 to the x equals 8. 2 to the 3 equals 8. Therefore, x equals 3. That's not as nice because it doesn't flow, and it might be clearly communicated and everybody kind of understands it, but when they start to get harder, you can't solve them this way, so it's not good enough to solve them that way. So don't do it this way. The x should be on every line, and if you just get used to it, and some of you probably were still doing this at the end of grade 11 because some people, it doesn't quite click with the difference between one way and the other, but don't do it that blue way. Do it the right way. Any questions? We're just going to do a bunch of examples, as many as we can fit in. Questions, questions, questions. All right. So, go ahead, try B. We're rewriting in exponential form. Easy one. And again, all I can tell you is, learning a new notation, it is relatively simple because you are, how hard is that? 3 squared is 9, my gosh. The math itself is super easy, but when you have to do the notation by yourself, so without following me or without having it being fresh in your mind, it's hard, right? It feels fresh and it feels clear right now, but 2 hours from now you'll be like, wait, what was it again? Where does all the numbers go, right? You'll sort of forget it quickly. So you got to really work with it over the next few days. And this is, I would say, because the notation is so new and this operation is so new, that if you're ever going to do homework throughout the unit, like now's the time. Put in some time now to really get the notation, and that's going to make everything else we do throughout the unit a lot easier. Okay, next one. This one's a little bit different because I got a fraction. So the other thing we're doing today is we're sort of reviewing how fractions are like and exponents are related to each other, how that whole thing goes. But first thing we have to rewrite this in exponential form. So the base stays the same. The base of the log is 4. So 4 to what exponent gives me 1/4? That is what a logarithm is saying. What exponent on the base gives me this, the argument, which in this case is 1/4. And the last question was 9. What exponent on 3 gives me 9? Right? Base stays the same, other two things flip. So what is it? Who knows? Answer? Set 1/16? Try that on your calculator. So 4 to the x equals 4 to the 1/16. Do 4 to the 1/16 on your calculator. Did it give it to you? What do you think? -1. So this is, hold on, now try 4 to the -1 on your calculator. You should get 0.25. So what you were thinking of, I think, is this idea that the square root of 16 is the same as 16 to the 1/2. So you were on the right track. See what I mean? Which is 4. So that's the relationship there. So I can rewrite roots as fractional exponents, and that is something that we're going to see in this unit. But then 4 to the -1 is 1/4 to the +1, which is 1/4, or 4 to the -2 is 1/4 squared, which is 1/16. So if you want to write those down and refresh yourself of those little rules from grade 11, that's stuff you've already learned, but that's going to be super important. Like, we're reviewing it a bit today, but basically you need to be able to do this stuff starting now because the questions are going to have these. Good, so therefore my answer, sorry, I'll put that back up, is -1. And let's be honest with each other, you have calculators that do logs, right? So you can evaluate these without any understanding. You find that button if you have any kind of newish scientific calculator. The really new and fancier ones, you can even input a base. Some of the older ones, you can't change the base. So we'll talk about this. I don't know if we talk about it today. I'll mention it right now, though. But when it's just log, if you just go log of a number in your calculator, that always means base 10. Okay? Actually, I should say almost all calculators mean base 10. Sometimes when you do that on a computer, it means a different base, which we'll hopefully learn about a little bit in this course. You'll learn a lot about in calculus, calculus, but don't worry about that for now. So log with no base implies base 10 typically. But if you have a fancy calculator, you can input the base. And so then I would encourage you to do that. Log base 4 of 1/4, hit equals, and the result on your calculator should say -1, right? Any questions? Okay, let's keep going. Okay, so I'm going to rewrite this. Easy enough. Do you agree? Okay, next one. How do I rewrite -100 as a power of 10? You can't. negative 10 all squared is positive 100. So that's not possible. So this has no solution. So logarithms and negatives have a very tricky relationship. Because if the exponent is a cube, you can do it. And the base of an exponent can be negative. So then you would think, well, the base of a log could also be negative. And I mean, in some cases, you can kind of like reason your way through it. But typically what we say is the bases of logs are not negative. And we say that the argument certainly cannot be negative. Like some cases with the, we'll talk more about this as we go, but in some cases at least, it's not possible. But then in some cases it is. So they have a strange relationship. So not possible. So this one has no solution for x. And try it on your calculator, see what you get. Where's my calculator? Mine has two buttons there. So mine has a log, which is just log, so that would always be base 10. If I put in 100, it'll equal 2. I know you can't see that, but it does. Okay. And then mine has another button up here, which has like a couple little squares, so that's the one where I can change the base. So log base 10, it's still that. Negative 100. Math error. What about log base 10 of negative 1,000? Because could you, negative 10 cubed is negative 1,000. And yet I put it in my calculator, it still gives me a math error. So this is what I'm saying, like it's sort of a tricky relationship that they have. All right, let's try another one. The other thing that can be really useful is as you work through this, I can guarantee you, you will start to think in logs. Like your brain will start to think in logs, not always translating to exponents. Okay? But if you ever get stuck, or you're ever not sure, or you ever start to confuse yourself or overthink something or whatever, then you can always go back to rewriting it in exponential form. Right? That's always like, it's nice to have a default fallback position, a net to fall back on, that kind of thing. So 1/3 to the x equals 9. What's this one? Negative 2. Because the negative will flip it. And then the 2, well, wait a minute. If I do, so 1/3 to the x equals 3 to the negative 2. So 3 to the negative 2, sorry, 1/3, not 3. Will that give me 9? That's the question here. So off to the side, I'm just going to do a quick check. You could check it on your calculator too, of course, but I'm going to do a quick check. So, and this is how we would do it in grade 11. I flip the fraction and get rid of the negative, right? So this equals 3 squared. So it's to the positive 2 now. And I took the reciprocal. And so sure enough, that's 9. Before we move on, I don't think it's going to come up today, but while we're refreshing all the stuff, we might as well. What if it was 2/3 all to the negative 2? That's equal to 3/2 all squared, which is 3 squared over 2 squared, so 9/4. But right, so you flip the whole thing. Often we see the 1/, and then people don't know what to do if it's a more interesting fraction. Okay, good. So what's different about G is it doesn't have an X. So this is where, and you don't have to do this today, but if you're working through the homework and you find yourself starting to be able to, then I would encourage you, like, one of the main reasons why we rewrite an exponential form, yes, it's something we want to be able to do anyway. Okay, it's an important takeaway from today for sure. But we're doing it until we get comfortable enough to just start evaluating. So if throughout the homework you start to get comfortable enough then start trying it. I would start doing that, right? Start asking yourself, what is the question that this is actually asking, and then just evaluating. There's a couple of questions. There's a long, I think it's question number 5 in the homework that has a whole bunch of examples, like up to M or something. And near the end of that, some of the questions get a bit more complicated, and it gets harder to use an X in them. So for those ones, you would start to see that it's easier not to use an X and just to evaluate. But I'm going to show you a couple of tricks for that. So does anybody know what the answer to this one is, first of all? 6. How'd you get that?
I figured out the one thing on the calculator.
Oh, okay, fair enough. Very good. What does that mean? What does it mean, John?
2 to the power of 6 equals 64.
Right, 2 to the 6, 64. The question a logarithm is asking, what exponent do I put on the 2 that will give me 64? So this is interesting because I could also, instead of rewriting it with an X, I could just leave it as a log and then rewrite the 64 as an exponent of 2. Like that's what we would do anyway. So this is 2 to the 6, and there's a property that we're going to learn actually probably tomorrow, where since this is saying what exponent do I put on a 2 so that it equals 2 to the 6? Well, 6, right? Like if these numbers are the same, then the answer has to be the exponent. But if you don't get that just yet, that's okay. We're going to look at that again. That's a property eventually you have to know. But if you start to think about what a log is, then you'll get that. What exponent do I put on 2 to give me 64? What exponent do I put on 2 to give me 2 to the 6? If I don't know if you want to write this down because it might muck up your stuff, but you can just watch for a minute. If I did this, if I did it the other way, if this was equal to x, see, it's not equal to x. So I would have to say, like, let x be log base 2 of 64 to introduce the x. It can't just magically appear, okay? But if it had an x, this is what we would do. We'd do 2 to the x equals 64, and then we'd rewrite 64 as a power of 2. 2 to the x equals 2 to the 6. And if that's true, then x has to equal 6. So all I've done is the same thing here, just leaving it in logarithmic form. Do you see what I did there? Okay. Almost all the questions you can solve without that. But by the end, if you feel like you're starting to be able to not have to rewrite in exponential form, I would encourage you to do that. So for this one, log base 4 of 64, how do I write 64 as a power of 4? 4 to the 3, good. And so then that's, what exponent do I put on 4 to make it look like 4 to the 3? 3, obviously. That's not what you were going to say, though. Go ahead. You are going to be required to solve these without a calculator on the quiz. So I would, thank you for asking. I would strongly, strongly, strongly encourage you not to use your calculator for any of this work today. Check with your calculator. Don't depend on it. Because we're going to test you without your calculator, like we did back in trigonometry. And we're going to do harder stuff that you have to be able to do this in your head anyway. Like you have to come to terms with what a logarithm is and be able to read it for what it is. And if you just depend on your calculator, you're never going to get there. So I would say don't do it that way. I would say show some steps, do some thinking around it. That's what's going to get you to be successful.
But if there's looking just write the answer out, they want to write out steps.
I would say for today, yes, but eventually no. I would say for today, yes, because rewriting it as an exponential form is understanding. It is a skill you have to be able to do anyway. And rewriting it like this is a great skill to be able to do, to just see it and understand it, the notation and all that stuff, and start thinking about logarithms. So for today, I would say yes. And then maybe even tomorrow, I would say yes. And then after that, okay, I got this. And yeah, we start to sort of speed up the process and not show all the steps. That's right. Because ultimately, that's right. That's what we're doing. Like ultimately, the logarithm is an operation, just like 3 squared. I do it and it gives me 9. I don't write out 3 times 3 which equals that. Like I don't write out what it is. We used to do that because we were learning, but we don't do that anymore. So ultimately, log base 4 of 64 equals 3. Like that's where we want to go with this, for sure. Do I have another one here? Yes. So how would I rewrite this one? I would do log base 1 over 8. And then I want to write 1 over 8 with some exponent. So I need to flip it because 64 isn't a fraction, so I need to flip it so it's going to be negative. And what exponent do I put on 8 to give me 64? 2. And so this equals negative 2. Any questions? I think we got a couple more examples and we're going to do a little bit of graphing, but that's basically like the different kinds of questions we can see. Okay, I want you to try this one. Try all 3, actually. I'll put all 3 up. Oh, there's only 2. Yeah, there's only 2. Try those 2. Again, sometimes all of a sudden you're thrown a curveball and you're like, I was getting this, and then now this one is making me think. So use one of the other strategies. Rewrite it. You can't even add for this, just add an x if you want, equals x, and rewrite it that way if you want. That's fine. However you want to do it for right now is okay. All those little things that we say, the base stays the same. What's the other thing we say? Like, what's the question that the logarithm is asking? So that first one is asking, what exponent do I put on 10 so that my result is 1? Hey, what is it? 0. How many people got 0? A lot of people I saw. Very good. So this is log base 10. Whoops. Base 10 of 10 to the 0. Because 10 to the 0 will give me 1. And so then the answer is 0. Or if I was doing it the other way, it'd be 10 to the x equals 10 to the 0. Therefore, x equals 0. Right? But there is no x, so that's a little bit weird. Like this is the problem, is there is no x. Okay, so yeah, like you got to be aware of that. This would actually not be a totally appropriate way of solving that question if you were given that question on a test. X equals 0. What x? What in the world are you talking about? There's no x in the question. So just be careful. Those are some of the smaller details that we want to do. Oh, there is another one. For goodness sakes. What about this one? What's the answer to this one? Who's got it? 4. So log base 5, 5 to the 4. And you can do 5 to the 4 on your calculator, and it gives you 625. So therefore, my result is 4. Very good. One more. This is the only one like this I think that we have. What exponent do I put on 1,000 to turn it into 10? For those of you that don't have a calculator that will do it, there is something that you will learn. So don't worry. You'll still be able to use your calculator to evaluate all kinds. Okay? Not today, but you will learn how to do that. So don't worry. You'll still be able, if you have your calculator, but we're going to test you without a calculator anyway. So anybody know what the answer to this one is? 1/3. So if I take the cube root, right, because the relationship is 10 cubed gives me 1,000, means 1,000 cube root, or 1,000 to the 1/3. And so then that equals 1/3. And so if you can do that on your calculator and you try it, we'll give you that answer. So there's your fractional exponents, negative exponents, and new notation on logarithms. I don't know how you're feeling about this, but it's very new and the notation is a bit strange, but this is a unit that you can see a lot of success with practice. It takes practice. It might seem simple and obvious, but it's not, right? Because it's so new, like I said. So you do need practice, but this is a unit that I've seen lots of people have good success with. So it's kind of nice. We're getting close to the end of the course. Next unit as well, which is our last unit, you can certainly be successful, but it's got some slightly harder thinking in it. And it's got a lot of algebra, but if you're good at algebra and you practice, you'll be fine at that part. But it does have some harder thinking in it. But this unit, it's really just notation and learning the laws and practicing and making sure you can do the different kinds of questions that we're going to do. Okay, let's see if we can get through at least one of these. Consider, what is the inverse of y equals 2 to the x? Who remembers from yesterday how we algebraically find an inverse of something? What's the trick?
Switch the positions of the y.
Very nice. Okay, so I'm going to switch the positions of the y and the x. So I get x equals 2 to the y. How do I rearrange this now to say y equals? It's a tough question. Does anybody know? With logarithms, of course, that's what we're doing. Very good, and you even gave me the whole answer. So the base stays the same, log base 2, and the x and the y switch places. So now the y is on the equals, and the x is the argument. Very nice. So the graph of y equals 2 to the x, and the graph of y equals log base 2 of x will be the inverse of each other. And we know something about the inverse of a graph. So let's sketch this. So I know that 2 to the 0 is 1. I know that this, I'm going to use a different color, green. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Oh, my scale that's not right for the scale. Whoops. You can just sketch. You don't have to do it perfectly. So this should be 2. And this would be 4. Oh, geez, no. This one's 2. There we go. And this one's 4. I think that's right. As long as I'm consistent, I'll be fine. And then 2 to the negative 1 is a half. 2 to the negative 2 is a quarter and an eighth. I'm going to add a few points, but we know that those get small really, really quickly. And that's what an exponential graph, this is y equals 2 to the x. So the inverse graph of that is reflected in that line y equals x, which is given to us there, that blue line. And then, again, I can interchange the x's and y's. So if this was x is 0, y is 1, this would be x is 1, y is 0. This was x1, y is 2, so x is 2, y is 1. X is 2, y is 4, so x is 4 and y is 2. And then these ones are going to go down like this. So if the exponential function has an asymptote of y equals 0, that this parent function, no transformations, approaches that asymptote, what do we know about the graph of y equals log base 2 of x? it's got an asymptote here, which you can see, and it makes sense. And if you think about logarithms, like spend some time thinking about it, you can make sense of it. But it also just makes sense in terms of like, the relationship between domain and range and how we flip things, right? When we take the inverse of something. So there you go. That's what a logarithm looks like. A logarithm, in some ways, looks like an exponential function graph, but it's been reflected. And make sure, something weird about my graph there. It's wrong. Yeah, one of those points is off. Make sure that you get familiar with what a log function looks like. We're not always going to graph as an inverse. We want to just kind of know what its general shape looks like so that I could graph a few different functions. Okay, so then quickly, if you just want to watch, I think that's fine. I don't know, you can sketch these into your notes if you like, but I know you don't really have a grid. What about 1/3 to the x? Well, that's the one that's flipped. So it's like 3 to the x, except it's flipped around. So it's going to be, goes through 1, and then 1, 2, 3, and then it's going to go off the graph, and it's going to go like this. And so, so this is y equals 1/3 to the x. And so then the reciprocal of that is going to look like this. And I'm going to take this point, which is -1, +3, and I'll go +3, 1, 2, 3, -1. So this one's going to go like this. Something like that. So this one is y equals, I'll do it over here. Y equals log base 1/3 of x. Any questions? There's a couple little graphs like that you're supposed to sketch just to get familiar, but they're not really with transformations. I don't think they're just simple like that.